So this morning we are starting with a short science session. We have a talk from LHC, followed by a talk from Livermore. The first speaker is Stephen Gowdy from CERN, working on a CMS experiment. So Steve, welcome.
So good morning. So as Jacek says, I'm from CERN, and I work on the CMS experiment, and I'll tell you a bit about those shortly. I'm going to try and sort of theme this talk on a recent publication that we had. And I'm saying the Higgs because we're not calling it the Higgs yet, but we found something. And I'm going to tell you a bit about how we do that. And so I'll take you through, give you some background on what the LHC is, then the experiment I work on, CMS. There's a bit about the challenge that we have in trying to analyze this data, and say how we do it, and what resources we use to analyze the data. And then tell you how we organize it, some techniques that we use. And then as it's a database conference, I thought I would say what we use databases for, and then close with some future trends. And so the Large Hadron Collider, this is quite a large machine. It's in a circular tunnel, 17 miles long, or a circle. And it's 100 meters underground. And it crosses the French-Swiss border. The protons that get accelerated in here travel almost at the speed of light. It's almost, they can't go at the speed of light, but they get very close. And if you can work out how often they go around this circle, and so they cross the border 11,000 times a second. Luckily, they don't need to show the passport. But we actually won't reach our design beam energy until 2014. We have a long shutdown. We call it long shutdown 1, anticipation of more, to upgrade the machine. It starts next year. But in the machine, we can potentially have interactions every 25 nanoseconds, which means 40 megahertz. But what makes it even more interesting, and I'll come back to this, is that each of these interactions can have multiple collisions. And we call this pile-up. And at the moment, we get about 30 interactions per event. And so this is what the Accelerator Complex looks like. The LHC is only the last of the machines that have been built at CERN. And the way it generally works is the older machines feed in the beams into the newer machines, which makes them, it increases the energy as it goes along. And so the protons that go into the LHC actually start at LINAC 2, go in the booster, get sped up a bit, and then around the PS, faster again, and then into the SPS. And when they come out the SPS into the LHC, they're going about 450 GeV. And then then the LHC itself accelerates them up to, at the moment, 4 TeV per beam. Now because of the way this works, that means we have to fill the machine. And typically, we fill it once per day. So this is, if you looked down and you could see the machine, I mean, you can't because it's underground, but if you could see the machine, this is what it would look like. The CERN main site is this triangle here. And that's the large, well, the oldest, no, sorry, apart from the LHC, the machine that's still used that's older than the LHC is the SPS. And that was quite big. There's another CERN lab here. It's Prevesan. As you can see, the airport, Geneva Airport, Lake Geneva, the Jura Mountains, and the Alps are just off the picture here. But the CMS experiment I work on is way over here, at the other side of the ring. And it's a 20-minute drive to get there. So you really have to want to go. We have like a sort of satellite control room on the main site, so people don't have to drive out there all the time. So CMS, this is what it looks like. It's a typical high energy physics experiment where we try to cover as much of the solid angle around the interaction point as possible. Near the center, we have high resolution silicon tracking detectors. And then we have what's called an electromagnetic calorimeter, hadronic calorimeter, and I'll come back to this. And then a solenoid, a big magnet in a cylinder shape. And then muon detectors around that. And you can get this idea of the scale by a sort of small person here. So this is like a slice through the detector. And this is basically how we do particle ID at sort of basic level. You can see here there's sort of 5 different categories of particles. The high-resolution silicon trackers near the center. And then the first interesting thing that happens is things hit the electromagnetic calorimeter. And sort of electromagnetic type of particles will usually stop here. And that's the photons and the electrons. And then we can tell them apart because it's only charged particles that deposit energy in the tracking detectors. And so you can see the electron. You can see this is an electron here. Has a track and energy that matches up in the calorimeter. And then there's a photon here that we don't see until it deposits energy in the calorimeter. And then the next interesting detector is the hadronic calorimeter. And here, as you can imagine, the hadrons deposit their energy, generally. So this is a neutral one. Again, it doesn't leave any energy behind in the tracking detector. And so that's neutral. But here's a charged hadron that, again, curves in the magnetic field and leaves most of its energy in the hadronic calorimeter. And then the 5th type of particle, the muon, the experiment uses in its name, will generally go all the way through the detector. And you can see here, when the magnetic field is going one direction, it curves one way. And then after the magnet, when the field's going back in the other direction, it curves the opposite way. And this is a representation of how the data flows when it comes out of the experiment. So this is the detector here, and there's lots of electronic front ends where we buffer the data, because it's coming in at this huge rate, which at the moment the machine runs at 50 nanoseconds instead of 25. But there's still a lot of data gets buffered here. We have long enough buffers that we can take about 3 microseconds to make a decision if we want to keep this event or not. And so there's a hardware trigger, and I'll show you some more about that in a second. And then it comes down into a filter farm where there's sort of software filtering done. And so this is a bit about how the sort of hardware trigger works. It has to look at only small areas of the detector. It doesn't have time to try and correlate different parts. And so it looks at energy in the different calorimeters to try and just decide if there's interesting energy or missing energy. And it also tries to make muon tracks from the muon detectors. And then both of these sets of triggers feed into a global decision. And if it's decided that, oh, this is an interesting event, then it will read it out. If it's not, it will just fall off the end of the buffer. And so if you try and think about the data rates coming through this thing, the sort of zero suppressed and compressed event size is about a megabyte. And as I mentioned, the collision rate is 40 megahertz. So that's 40 terabytes a second that we acquire data at. I mean, it's probably actually a lot more because this 1 megabyte is heavily zero suppressed by the time it comes out of the detector. So the buffers are actually a lot larger. But not all the detectors do read out at this speed. We have to sometimes have events that are shared. But the hardware trigger then has an output rate of about 100 kilohertz. And as I mentioned, it can make this fast choice by only looking at certain detectors, not the whole thing. And so the data rate out of here is about 100 gigabytes a second. And that's what then goes to this high-level trigger done on a filter farm. And the filter farm is just like a cluster of Linux machines. It's quite large, but we'll talk about that. I'll come back to that right at the end. And the nominal output rate is 300 hertz from this farm. Although due to the shutdown next year, we've actually been running at 600 hertz, and with the intention of analyzing a lot of this data next year. So some of the challenge. Now this is one of the candidates that was used in the Higgs paper. It's a very easy one to see. The collision happens here, and then you see 4 muons come out. They go all the way out to the muon chambers. And here's another sort of representation of what happens. You can see the proton beams coming in, the silicon detectors. They hit. Now the beams are actually long, and that's how you get more than one interaction. And then it goes the muons. So that looks very clean, but in reality, this is what we get, where we have lots of interactions in the same event. And so this was actually a high pile-up run from last year to try and just make sure our software scales to higher pile-up rates. We didn't want to suddenly hit a brick wall. And so this had 40 reconstructed vertices, so 40 different events inside one readout in 25 nanoseconds. And so that was one event. This year, by the end of this year, we should have about 7 billion events to look through. And again, this is after the reduction from 40 megahertz to about 300 hertz. And it doesn't include simulated data. We also create to try and understand what actually happens in the detector as the particles go through it. If we believe the sort of predicted cross sections from theory, in this data set there should be something like 500,000 Higgs particles defined. But the vast majority of them are much harder to find than these 4 leptons, 4 muons. And so how do we actually carry out our computing? We use what we call the grid, and the name for the whole thing is the worldwide LHC computing grid. And it's a tiered system. We have the tier 0 at CERN, where the data gets sorted, and then the first pass reconstruction. And then there's a set of tier 1 centers, where these are large regional facilities. There's one in the US for CMS. And these also provide tape storage. So there's one set of data. The data gets saved twice, just to make sure we don't lose it. It's quite precious. It's quite expensive to get, so we don't want to lose it. So there's one copy kept at CERN, and there's another copy kept at one tier 1 site. And then there's also tier 2s, which are frequently universities or sometimes consortiums of universities. And there we do the simulation, and this is usually where the end user analysis gets done. So again, you can see this is the way the data flows through the system. It comes out the detector into the filter farm, and then it gets processed in the tier 0, and then it can get fed into all the tier 1s. And in a sort of traditional grid approach from many years ago, there would also then be a set of each tier 1 would have a cloud of tier 2s and tier 3s that it feeds. But in CMS, we've went for a sort of full mesh model where any site can transfer to any other site and get data from any other site. Although we don't allow any tier 2s to go to the tier 0 directly, just because we want to keep that safe. It's precious. To try and make sure that we can get the data out to the tier 1s, because this is really quite important that we have another copy of the data. We have a LHC optical private network, and this is a schematic of it. We have CERN at the center, and then there's all the tier 1s for all the different experiments, not only CMS. And the CMS ones have this green flag on them. And the data rates through this thing this is just one day last week when I looked. It's like 30 gigabits a second out of CERN and 15 in. Although you can see from the picture that the data coming into CERN, some of it will be going between tier ones. It won't only be data that actually stays at CERN. It will just be transient. And so the resources that we have across this entire WLCG infrastructure is this for by the end of this year. We measure CPU performance in kHz 06, and this is just a benchmark that's meant to follow our applications better than the more traditional spec int. But that's where it works out to roughly in kilospec int 2Ks. And we have about 50 petabytes of disk and 90 petabytes of tape. And as I said, there's no tape at tier 2s, but the tier 2s make up more than half of the rest of the resources. And this is where the vast majority of users run. And there's about 50 tier 2s in CMS. And so how do we organize the data and make sure we access it efficiently? The things that comes out of the filter farm are called streamer files. It's just a name, it doesn't really matter. But the idea is that it can stream them fast without too much bottleneck to make sure we don't slow down the data acquisition system by having to write complicated files. But then these get read in the tier 0 and reorganized. And so it reads in one particular set of streamer files and writes out another set of files that are in different primary data sets. And these primary data sets are based on trigger selections done already in the high-level trigger. But it's based on physics motivations. Like, for example, one of them is called double muon, where there's two high-energy muons. And this output is the custodial raw copy that goes to tape at CERN and another tier 1. And these streamer files just get deleted. They're just transient data. So once we have this raw data, and this is what is really precious and never changes, we then run the reconstruction on these raw primary data sets. And the output there then is the reconstruction objects, which is tracks with hits and lots of detailed information. And then also another separate file called the AOD, which is a much smaller subset and targeted analysis. And so, AOD just stands for analysis object data. The simulation also provides a similar set of files plus the truth information so you can understand exactly what happens in the event. But we also then order the data inside these files differently depending on how it's most likely to be used. We use a tool called Root as the persistency framework. Anyone in high-energy physics would know what Root is, and some other people use it as well. And so, as I said, depending on how we expect it to be read, depends how we order the data in the file. If for the raw in RICO, typically most consumption of those files will be read the entire event and do something with it. And so the events are grouped together in the file, roughly. So from the first event to the last event. Whereas for the AOD, a use case here would be you would pass over just one attribute, or a few attributes, probably, in the file, and make some plot. And so we cluster the same attribute together. It's not actually quite this simple, the way Root works, but more or less. Another thing we do to try and make access faster and more efficient is we skim the data. As I mentioned with the primary data sets, they use the trigger information to filter out events in different sets of files. But after the reconstruction, we have much more detailed information. And so we can apply a better knowledge on how we want to sort events for physics. And so folk can cut quite a bit harder, not too hard, because you don't want to obviously throw away signal events, but a lot harder than you would just with the trigger information. And we do the first set of skims at the tier 1 on the output straight from the tier 0. So as soon as it arrives at the tier 1, there's a job starts up. It's already been created. It's just waiting for the data to arrive. And then it launches in skims. And at the moment, we write out 81 different data sets based on the reconstruction output from the tier 0. So that's 81 different analyses, have their own very small subset of the entire data that they can then start to analyze almost instantly, well, very, very quickly after the data is logged. And so these data sets that I've mentioned are just collections of files that you should generally process an entire data set together. We do, to make them sort of manageable in size, we usually close a data set after 6 months or something. And then so when someone's doing analysis, they know they have to use run 2012A and run 2012B and 2012A and B and stuff. But this is one place where we actually use a database, Oracle, and that there's information about the data set and on its provenance, how it was created, the releases and the configuration and quite a lot of different things. And obviously they can be superseded, so we can also mark them as deleted or deprecated or whatever. But the end user tools, when a user wants to actually run an analysis on all the data sets, uses a tool that queries this database and creates jobs. And these, he runs one command, and then it will typically launch jobs at any site that has his data sets. And so usually it's a small number. We can't afford to duplicate them too much, but we also don't want data just at one site in case there's problems. A tier 2 is supposed to have an uptime of about 80%, and so having a data set at 3 sites is probably about right. So now just a little bit about analysis techniques that we use. So each analysis will find its own way of separating a signal from background. One thing that you might think about doing is looking at the energy of a muon, for instance, and this is just a made-up table. And you can tell in the detector how the momentum of the muon by how much it curves in the magnetic field. The straighter it is, the faster it's going. It doesn't curve as much. But let's say this was the distribution for your background, and then there was a distribution for your signal. Then you decide somewhere to put a cut. And obviously, if you move this cut more to the right, you get a purer signal over background, but you also cut out a lot of your signal. And so you have to optimize either the signal over the square root of the background or signal plus the background, depending on if this is a new discovery or you want to analyze it in more detail. So this is like sort of most basic thing that people might do. But then a lot of the analysis these days are based on multivariate analysis, and there's various different kinds. I think one of the things that's interesting is that we have now some packages that you can apply all of these to. You feed it in the training sample, and then you get it to run over your data. And this is one of them, TMVA, which stands for Toolkit for Multivariate Analysis en route. And so you can see here the 4 different multivariate analysis techniques on the same input test data. And you can see which one helps separate your data better. And so in the Higgs paper, one of the modes looked at is this Higgs to 2 Zs, then each Z goes to 2 leptons. And in this case, the interesting discriminators are the 5 angles in the decay. And and the masses of the two Zs. And that gives quite a good separation. And so this is one of the plots from the paper, and there's a reference at the end. And you can see this here is what we believe, what we probably think is Higgs. So now a bit about how we use databases. And none of them are really that large, to be honest. So our largest database use, and not in size, it's only 300 gigabytes, is the conditions data. And this provides the geometry, how the detector is laid out, the alignment, how the different parts are placed relative to each other, which can obviously change with time. And the calibrations of the detector. If you deposit a certain amount of energy, you get a certain electronic pulse. And these things, you need to figure out the relationship between those. And again, it can change over time. It does change over time. Now, what makes this database interesting is that it gets used by just about all the jobs that run in the entire world by CMS. And this is typically more than 100,000 jobs. To try and allow the database to cope with this number of clients, we use a set of SQUID caches. And the database queries from the jobs get transformed just into a HTTP request that goes to the cache. And then this cache then queries the site at CERN. I've got a picture on the next slide. And the technology we use to do this is called Frontier, which was created for CMS and another experiment. It was at Fermilab, CDF. And this kind of only works because the data is only written really at CERN, but consumed everywhere. And so you can just focus on the top half of this, which is the offline database, which all these 100,000 jobs will then use. There's an offline Frontier server at CERN and a top-level SQUID. And then there's a set of SQUIDs at CERN for the tier 0. And then I think this isn't working so well. Then all the tier sites then have their own set of SQUIDs locally. But what's quite interesting is if you sort of add up the entire rate over all the SQUIDs, there's something like 500,000 requests per minute to this set of SQUIDs, or 500 megabytes a second. But by the time it gets to the offline server at CERN, it's down to 4,000 requests per minute and only half a megabyte per second, which is not much. And so it just shows you how much of the queries are similar and sort of redundant. Some of the other databases we use, there's one it's called FedEx because it's for moving stuff around. I guess that was a nice name. And so it manages all the file transfers between all the different sites and knows what files are on what site. It handles the deletion as well and things like that. And that runs out of a single Oracle instance at CERN. And then the thing that does the database bookkeeping system is called the database bookkeeping system. Not very imaginative, but okay. So that contains all the metadata about datasets and files. And the main instance of that is at CERN in Oracle. However, we do support MySQL as well, so that analysis groups can have their own server where they have their own data. We also have a few different job tracking databases, and these use both Oracle and MySQL. And then recently we've started using CouchDB for archiving some information about jobs after they've been run. But if we look at the Oracle instance at CERN, the offline one, you can see the data rate out of it is something like 6 terabytes a day, physical reads, but the logical read rate is much higher. So I guess this also tells us Oracle's doing a good job optimizing that too. So future trends, future looks bright. So one of the things we're doing is what we're calling federated storage, where we want to try and make all of the entire storage system visibly globally through one window. And we're using redirectors, a particular technology that is quite interesting for me because we developed this on a previous experiment at Babar at SLAC when we were getting rid of the big database that was mentioned. It's called XRootD. But to show you how this basically works, if you have a user application that wakes up somewhere inside the US, it knows that it should contact the US director, and so it says, open this file for me, please. The US redirector then goes to all the sites that are registered with it and says, do you have this file? For this example, we'll say like, none of them do. It's probably unlikely, but let's just go with that. And so then the US redirector says, I don't have it, go try the global system. So then the job goes to the global redirector. Again, I want this file, please give it to me. The global redirector then goes and asks the EU one if it has it. If we had other regions, it would ask them as well. We don't at the moment, but we might have an Asian one eventually. And then again, the EU redirector then goes to all the sites it has. It turns out Site C actually has this file. So that information gets passed back up. But the EU redirector knows that Site C has it. The global redirector knows that the EU redirector has it. And so then it tells the job again, go to the EU. Job goes there, and gets told, sorry, go to Site C, opens it here. And then in reality, what would actually happen, there'd be another one of these very quick loops where the site redirector would say, go to host X that actually has the data. And there would be a direct, there would be no, the end user job would read it directly from the host that actually has it. And you can put proxies in if there's network firewalls or whatever, if you need that sort of thing. So another thing that we're looking at for the future, both long-term and medium, are clouds. There's a European initiative that's been going on for 6 months or something called Helix Nebula. And I think one of the things that we take away from this is there is a need for having some sort of unified interface. Because testing, I think it was 4 different providers. Each one is slightly different, and so it takes you a long time to actually start doing something new or do anything with all the different providers. We've also had a sort of proof of concept on the Amazon cloud where we've run CMS jobs there. However, the cost is still quite expensive. It's not completely obvious by how much. I mean, something up to an order of magnitude is probably between 5 and 10. So at the moment, running our own data centers is more cost effective. I mean, we do share our data centers with other experiments, and it's probably a lot of the reasons why. Although it could be, this sort of thing could be interesting when we have a conference deadline and we need to generate or reprocess the data very quickly. Then it could be a way of adding capacity. But in the sort of more short term, there's sort of internal clouds that we're more interested in. CERN at the moment is trying to move to what it calls an agile infrastructure. And one of the big motivations for that is that they're going to open a new data center in Hungary. And they intend to operate it just like the data center that's on site. So there would only be people in Hungary that like turn the boxes on and do that sort of thing. All the sysadmin stuff would be done from Geneva. And so they're looking at OpenStack as well. And so that's one of the reasons next year, during the long shutdown, we want to use the online filter farm, which is quite large, something like 15,000 cores. And so we're also going to try and deploy OpenStack on that to allow the offline applications to use it. One of the benefits of using a cloud system is that it can be redeployed quite quickly for different uses. the setup for offline and for taking data is quite different, and they will need to take some data for when they do things to the detector, upgrades or repairs. They want to make sure it still works after they do that sort of thing. So just to summarize, we do use database technology in quite a lot of different ways. It's not huge though. It's only about 10 terabytes if you add everything up, and it grows something like a terabyte a year. Or two. Our big data is our raw data, which is in these root files, and that's something like 20 petabytes. But CMS uses a global, worldwide computing infrastructure to deliver our physics results. And the takeaway thing, I guess, from this publication in July, or that was submitted in July, is that we found a needle, and now we need to take the rest of the data for this year to try and figure out which kind of needle it is. And if you're interested in reading the paper, this is the link to it. So just one thing before I stop talking. As you heard, the XLDB Europe will be at CERN next year, and CERN's very happy to host it. They've booked a room that's really quite nice with good views if the clouds aren't too low. Otherwise, you'll be above them. These are the dates that it's expected to be. It's during the LHC long shutdown, so there'll be a lot of work going on to try and get ready for the upgrades. And it'll be an interesting time to talk about data management. And so if folk are interested, they should contact Dirk at CERN or in Jacek. So I'll just leave that up and then ask if there's any questions. Thank you.
Think you can run data centers more efficiently than Amazon, Google, or Microsoft. And it's really, physicists are really smart people, and I know they think they can do data management better than the database community, and I guess now they think they can do clouds better than the major providers of cloud infrastructure, who manage to keep data centers not with, 15,000 cores you think is a big number, but our data centers have 100,000 machines with almost 1 million cores in them. And yeah. I don't know why you guys are wasting your time doing this kind of grunt, moving data around the world, worrying about replication, GODR. It's just not, it's not a good use of the physicist's brains. I don't understand this at all.
I mean, well, for me, then, yeah.
You have to negotiate.
Yeah.
That's really, I think, if you need a major provider in negotiating, you're not counting your manpower is what you're not doing. So
no, the difference between the factor of 10 and the factor of 5 is the manpower. And even a factor of 5 has been quite generous with the manpower. And so there is, the prices that we see, at least, there is still a way to go. But, yeah. Yeah. Yeah.
It's machines and bodies and pipes, and it's all the same, right?
Yeah, that's interesting.
I really challenge your numbers, and I really think you should go back to the vendors, go to Google. You don't have to go to Microsoft. Go to Google. Go to Google. We want to leverage your capabilities and not do this ourselves, so we can focus on the science.
I'm having lunch with Google, actually. So.
Okay.
Any other questions or comments? Yes, just wait for the mic.
I'm not sure which cloud service provider the previous gentleman was asking from the perspective of, but I was curious, you chose OpenStack as the platform for the 15,000 core cloud. Could you provide a little bit of insight as to your selection of OpenStack, and also any data gravity issues around how much bandwidth you need into that OpenStack cluster or out of that OpenStack cluster to support your requirements, which may or may not affect your ability to use a public cloud? Thanks.
I mean, I can't comment on the decision to use OpenStack. That was done by CERN IT, and we are just sort of piggybacking on what they're doing. I can comment on the data rates, though, because it's one of the things we worry about, is the data, let's see. The data has to go around this ring, and so we only have so many fiber optics that go around the ring. And so we have, for this rate, we have two 10 gig connections. And so we have to make sure for 15,000 cores that we can get the data over that. And it works out just about right. All the storage systems are here, and all the consumers would be here. And one thing that I didn't mention, and this is sort of applicable for this, but even more so for this wide area consumption of data, is that we've been doing a lot of work with root to make sure that the latencies don't kill you when you're analyzing the data. So to get that sort of data rate into a cloud would be quite hard, but then maybe we'd be storing all the data in the cloud in any case, in a sort of, if we imagined where it could be one day scenario.
Any other questions or comments? All right, okay, thank you very much.
Thanks.